Thank you, Hesjan, for the introduction. Yeah, today I'll talk about implementation aspects of lattice-based crypto. I do work on implementation, but not really. I don't really do implementation on hardware, but I do the designing parts for sure. But yeah, I have worked on the Cortex M4 implementation, but I'll not really go that much detail today. I'll stay more on, like complexity part for the time complexity, just for the first part of the, when we just implement for that part, and then I will go more details, a little bit details, when I go to secure implementation, as I have worked on that, So yeah, I'll start this presentation with this kind of outlines. So I'll give brief background. I do know, you guys already know, lattice-based key encapsulation mechanism and all, but I do need some of it, so I just briefly touch those. And then, yeah, polynomial multiplication, side channel attacks, its countermeasure, and the conclusion. So I'll start with the background. I'll talk about the LWE-based public key encryption and key encapsulation mechanism, and then I'll go to the parameter choices for two popular schemes. One is the standard, that is Kyber, and another is Saber, which was a third round candidate, almost standard, but yeah, it didn't get picked up later. So yeah, I'll start with the PKE scheme. Here we have, we have the, we have this seed that is sampled in the beginning, and that seed is used to sample the whole matrix. And matrix, you already got to know, for LWE-based scheme, we do need a matrix, a known public matrix, we do need a secret, and then we need an error vector so that we can create an LWE-based sample kind of thing. So A multiplied with S and E, where A is public and B is the resultant of this thing. When these two are public, if we don't know E, then we don't get S. It's hard. It's a hard problem, lattice-based hard problem there. And this is kind of a generic, construction which is used for every LWE or module LWE or ring LWE or LWR-based construction as well. So in that case, this E just gets swapped by rounding operation, where you actually scale down this A plus S factor from bigger modulus, which is Q, to a smaller modulus, that is P, where P is often divisible by Q because of we don't want biases. And then the hard problems remain secure. It's kind of a very basic thing that we need. And this is, if you check this key generation mechanism, then we have two random sampling. That is just random numbers, like uniformly random numbers, which we get from RNG. That is, we have to do. And then the next step is this generation of the matrix A. That is used to generate that, we use K-chuck, K-chuck-based pseudo number generator, that is XOF basically. And yeah, that is kind of an auxiliary function for post-quantum schemes, but it is pretty heavy from implementation perspective. And there is another thing that we need to generate secret and error, that is the spatial distribution that Leo talked in the first day. And this spatial distribution, often for most recent scheme, is centered binomial distribution. There is Gaussian distribution as well, but it's very hard to make them constant time. That's why people do use centered binomial distribution. That is pretty easy. And for centered binomial distribution, we just, for implementation, we just have to subtract the Hamming weight. So it's very easy and cheap algorithm. So the remaining part is this operation, this A into S plus E. So in this addition is still order of n, it remains cheaper, but this multiplication is the step. That is very expensive and native to this kind of operation. When we use just standard LWE, then it is a matrix multiplication. And when we, matrix vector multiplication, when we go towards module or let's say first go to ring. In the ring structure, it is a polynomial multiplication. And when we go to module structure, that is a that is still a polynomial multiplication, but we have to have that vector kind of form. So it's matrix vector multiplication, but with polynomial multiplication. So that's a kind of a very basic implementation strategy, what we require to implement this key generation mechanism. And if we go to the public key encryption, it's similar. We just need some extra thingy. That is, we do need a message. And for that, we have to encode the message to that most significant bit, and so that we can get back our message, that thing. And we do some compress operation so that our bandwidth remains pretty small, so that, yeah, to make our ciphertext size smaller, so that we have to spent less amount of time during communications. And that's how we get this ciphertext. And for ciphertext, first one, actually, this B prime is used, is the key part of this encryption module. And this CM has the message part, basically. And these are two parts of the ciphertext that we have to give, like that encryption module actually gives output. And the last one is the decryption one. And that one also have pretty similar operation, like you first decompress whatever you got back from the encryption cycle, then you actually do subtractions with your own key, with your own secret key S. You do the multiplication with the key factor, and then you do the subtraction from the ciphertext which has the message, that part, and then you get back the message. And finally, you decode it. Normally, this compress, decompress, encode, decode, these are pretty cheap operations compared to polynomial multiplication or multiplication operations. Like, long story short, here I just want to mention that, yeah, polynomial multiplication is one of the operations that is very expensive for any of these lattice-based schemes. And people have spent quite a lot of time to make sure like it remains very efficient or as efficient as possible. And yeah, and decompress and encode is pretty much similar kind of operation. It just has a little bit less, like it depends on the parameters of that, and compress and decode is similar. Now, if we check the final key encapsulation mechanism from that PKE, because yeah, PKE is kind of provides only your CPA security, it doesn't provide you CCA1. For chosen ciphertext attack security, it's kind of a must for key encapsulation mechanism to prevent a lot of attacks. So for KEM, we just use kind of for, like we use that popular Fujisaki-Okamoto transformation for this one, but for noisy variant, because LWE problem has noises, inherent noises, you can make perfectly secure scheme with it, but then parameter sizes goes very big. So normally people have some decryption failure, they still accept that. And you can make like, yeah, you still have security with decryption failure if your decryption failure is small enough, something like that. But if you check the key, if you check the key generation, it's basically the PKE keygen, except there are few hashes which you need, this hash, which you need to check basically for the later part, and you have an extra key, this jet, that is used during decapsulation failure basically. And that is generated during key generation, and it's stored as secret. Okay. And then you have the encapsulation. Encapsulation is also pretty similar as the encryption part. Here you just get the shared key out of the, like by doing some hashes here. And yeah, that's all you have to, like it's pretty much as expensive as PKE encryption, you just have few more steps. But if you notice, these are all hashes, you know. So these are not kind of LWE-based native operation, I would say, because a lot of people have already spent quite a lot of time to optimize the SHA-3 hash, which is Kechak. But for PQC scheme, people are more focused on, you know, optimizing its native components, and which is polynomial multiplication here. And if you check the decapsulation, it's similar. It just have two PKE operations. One is this decryption, and another is re-encrypting the decrypted message. And then you do the check. This check is, yeah, very hard to make sure it remains side channel secure. Yeah, it's just a side note, you know. So here also, this thing is, I would say, native to Fujisaki-Okamoto transformation, although it's not very expensive, but it's very hard to make it make sure that it remains secure. But yeah, it's just hashes and some checking, so it's not very expensive in a way. If you want to make sure like it remains physical data secure, then it becomes expensive, but normally it's not. So yeah, we have to we have all the schemes of key encapsulation mechanism. Now, if we see the parameter choices of Kyber and Sabre, where Kyber is the standard, which is currently known as MLChem. And yeah, this name is pretty new. And the hard problem it uses, that is MLWE1. And one thing we need to notice that its polynomial size is pretty small compared to the lattice dimension, because the dimension for lattice is 768. I have only put the secret level 3 one, not 5 or what 1. But yeah, it's similar, you know, if you understand this one, it's, it just scales up or scale down. They have 3 parameters just to make sure it remains very flexible for higher security, for lower security, or for normal security. And yeah, it is the normal one. Now, here polynomial size is 256, and that is what we need to multiply for polynomial multiplication, basically. We have to multiply to 256 length of polynomials. And then we have matrix vector with those polynomial size, but matrix dimension is 3 cross 3 there. It's not very big matrix, it's a small matrix. You just have very big polynomial. And one thing I would like to note you, that is that modulus that is used in Kyber, that is 3329. It's a prime modulus, which is a 12-bit number. It used to be a 13-bit number, but later they actually improved it by adding this 12-bit modulus. And yeah, it helped them a lot to reduce this public key size. And also they have introduced an extra compress modulus. It is kind of like they are also using a learning with rounding kind of thingy, just cut off some extra bits. They actually reduce the ciphertext size, basically. So in a way, they are also using kind of both of the problem, learning with error and rounding. But yeah, and also, yeah, another thing is like for the centered binomial distribution that I mentioned, for that it has like, for this variant, it has -2 to 2, kind of -2, -1, 0, 1, 2. These are the only possible values for secret and error. Sometimes error and secret distribution are not the same, but in this case it is. So I'll just focus on that. And if you check the Sabre parameter, it is pretty much similar, right? For at least for this ring and module structure, but it has different modulus size because it uses learning with rounding. So it has to be, you know, power of 2 modulus. It has to use that one. So yeah, that's the basic difference, I would say, you know, from Kyber, from parameter perspective. And you can see like that, yeah, you can see that key sizes is pretty much similar. For Sabre, you can store the secret key smaller size because you are not in entity domain and all those stuff. But yeah, it is just from the like overview perspective, it looks pretty similar. But we'll show differences later. It's just, you know, a disclaimer. Now, as I mentioned earlier, that is the thing, like in your PKE, the native operation, which is multiplication, that is kind of very expensive one, and people has tried to a lot of times to optimize it. So I'll talk about that. And just before that, I wanted you to notice that, yeah, for key generation, there is 1 multiplication. For encryption, it is 2, and for decryption, it is 1. But mind that, when we do decapsulation, we actually perform this decryption and encryption. So we have 3 multiplications there, basically. Like, and this one is vector-vector, but this one is matrix-vector, so it's more expensive because you have dimensional matrix multiplication. So yeah, that is expensive. So if we can reduce the cost of one polynomial multiplication, then this whole thing actually gets improved, right? So that's why people has tried a lot to improve it. And now I'll go for this polynomial multiplication part. For that, I only discuss school book 1, Karatsuba, Tumkuk, and entity. And then a variant of entity that is used in post-quantum schemes, basically. Yeah. With that, with further ado, we have school book multiplication. Who doesn't know that? Is there anybody who doesn't know it? I hope not. So what is the complexity of school book multiplication? Do you know, I guess? A hint? It's order of n. Okay, it's order of n square, sorry. Yeah, it is like you just do multiplication, coefficient-wise multiplication. It's very easy, and it's also very cheap in terms of memory, not in terms of time complexity, because you have to do all the multiplication and then you have to add them here. So it is expensive in that way. But you don't have to store any extra values or any extra thing. You don't have to remember previous things or any extra constant. So it is very efficient when you have like very small size of n. Let's say 16 length polynomials. So you do 16 cross 16 polynomial multiplication. It is pretty cheap, like compared to if you want to do any fancy multiplications. So do note that if we don't have any polynomial kind of or polynomial order multiplication, this is kind of best thing we have for smaller n's. And in hardware, it is very fast, because it's kind of, you can translate sometimes to shift and add kind of thing, so it becomes very fast. Yeah, that's all for polynomial multiplication. Oh yeah, for post-quantum schemes, we used this ring size, right? Which is zq x to the power n plus 1. And we have to do a reduction. And that reduction is like after doing the polynomial multiplication, we have to do that reduction, and it is it's just the subtraction, But yeah, when we add these things, if we have a prime modulus, then we have to do a reduction pretty frequently. And reduction algorithm, if your prime is not very structured, it's very expensive. It gets very expensive very quickly. So yeah, that's why if you have a power of 2 numbers, you can do school book pretty efficiently because you don't have to think about reductions and all those things. But if you have a prime modulus, then you have to think about reductions cost as well. So it becomes very expensive, very after a few steps, So yeah, with that, we'll go to the next one, that is Karatsuba. Do any of you know Karatsuba? Yeah, okay, cool. So Karatsuba reduces the multiplication steps. For the previous example what I showed, there was like 4, that has more coefficients. It's very hard to fit in a presentation, so I reduced the coefficient size of the polynomial. Now it's a 1-degree polynomial. If you use school book multiplication, you have to do 4 multiplications and some addition. But if you use Karatsuba, then you can reduce 1 multiplication at least. So it is helpful, right? It reduces your multiplication cost, like 1 multiplication cost, although it increases I'm not very habituated to this one. It reduces it increases 1 subtraction step, but yeah, you can do, sometimes, multiplication is more expensive than addition or subtraction in some, at least in some hardware. It depends on like how much bit you have, basically, like in your operand, basically. If it's 1 bit, then it doesn't matter. But if it is bigger number, then it does matter. But in like embedded devices, when you have that instruction set, sometimes sometimes multiplication cost and addition subtraction costs are pretty similar. So in that cases, it's not much beneficial when you use when you replace multiplication with addition or subtraction, but complexity wise it does matter. And now we have reduced this length basically. We have reduced the multiplications, number of multiplications with Karatsuba. And now we have a good algorithm to use with Karatsuba, that is divide and conquer algorithm. And that is used in like a lot of computer science applications, right? We do use divide and conquer whenever we can't think of anything fancy. Yeah, we do use it, and we get pretty good results with it. And there are a lot of analysis has been done on very optimization method to find the optimization method, find a good complexity with divide and conquer approach. There we have Master's theorem and all. So with that, actually, we use a divide and conquer approach on Karatsuba. If we do that, we actually can multiply bigger numbers, and I was able to fit at least 4 coefficient ones. There you can see, first we divide this big polynomial into 2 polynomials, similar for this one. Then we perform this multiplication step in another loop. This is the smaller multiplication part that I showed in the beginning, basically. It is a submodule for that, and then it gets back, it gives you back this answer from here, A to B, and you get this from there, you get this C2 and C0 and C1 basically, and you get the final conquer basically for these 4 coefficient polynomial multiplications. So with that, you can multiply bigger number, you have to apply it repeatedly. And with this, when you divide something, it's always good if we have power of like a divisible by 2 numbers, and if it is power of 2, we can divide like as many times as possible until it becomes 1, right? So power of 2 numbers has its own unique charm. So that's why it is used in almost every kind of cryptographic application. So like we do like power of 2 numbers. Yeah, after that I'll just show this master theorem. I don't know if you guys know or not, but yeah, this is the theorem. That theorem actually gives you pretty good complexity results, and it actually is used for divide and conquer approaches basically. If we have like a big problem, this is the big problem I have, and we can use a divide and conquer approach on it, and then if I have n size here in the big problem, and if I can split it to a sub-problems, a number of sub-problems, but each sub-problem has n by b n by b size. Here, please note that A and B is not always equal. I do know, like in some cases it is equal, but it's not always equal. And if we have that, and then we can go until that it becomes like length becomes 1 basically. And then we have like log NB kind of steps here. And then our time complexity, which is Tn, it becomes A into time complexity of the sub-problems plus extra function, which is Fn. This is an extra cost which we require to, do the extra outside kind of operations. Sometimes we do have a lot of outside operations, even though we use this divide and conquer approach. So they also think about that part. And if we have that, we can find complexity in this way. For us, this one is most interesting one, when we have A and B equal and our epsilon is 0. So yeah, then our complexity becomes this one. It is a tight bound. I'll not use that tight bound, which is theta, but I will use that order, which is I'm more familiar with, and I guess you guys as well. So yeah, you can see if we have this kind of A and B split, and our Fn is kind of like operation of n log B. B is the base. Okay, sorry, it's looks weird now here. B base A, and then our time complexity becomes n log base B A log n. Okay. So with that, No, I would also require this one. When we have a little less term minus epsilon, then I would have log BA base A. Okay, with that, I'll go to Karatsuba polynomial multiplication. For that, I'd get, if we apply this master's theorem on that, then our complexity becomes like this, because we split 3 times. Basically, we have to do 3 multiplications, and our size is 2. So it becomes, the complexity becomes order of n log 2, 3. Okay, and we still have to do this reduction part basically. Now, it is the Karatsuba. It is kind of very old algorithm, but later a generalized version comes into place that is called Tumcook one, that I'll explain later. And it is used in SABRE. It is very popularly known key encapsulation mechanism. And I have also designed a scheme with Tumcook-based algorithms, so it is very dear to me. And with this, for that, we need point value representation, because if we had point value representation of a curve, then we could do the multiplication in order of n time, right? Because we could just multiply in that way. We just had to do multiplication coefficient wise, and then we would get the new curve, right? It's very easy and it's very cheap. So, and its complexity is order of n. But how can we use it? How can we convert from a coefficient form to pointwise form? For that, we need some conversion algorithm, which will convert this coefficient to coefficient form to pointwise form, and then we will be able to do multiply, our nice multiplication that is just kind of like dot product or pointwise multiplication. And the last step would be point value to coefficient one, because we do want coefficient representation, right? So this, sorry?
When you do that, like you're basically doing the sampling in your small, so what are the constraints? Like what do you need to sample at a certain frequency, or like how do you decide where do you sample?
Sorry, like.
So when you're doing this kind of sampling,
yes.
So how do you design your sampler?
Okay, yeah, that's very important. Sample means like how I choose the points, right?
Yeah.
Here, it is random, like in the previous example I showed, it looks very random, right? But,
It's periodic.
oh, yeah, I agree. But we would like to choose as small number as possible, right? Because then we have less bits to operate on, and then it would become cheap, and we always want cheap things. That's the most important one. That's why we also take infinity points, so that we don't have to do coefficient operation. We just would take the constant term, like the highest term. Yeah, it's pretty, I would say, I will not go in that much detail, but here, you do know, right? Like if we have a degree 4 polynomial, to find that degree 4 polynomial, we have 5 unknowns, right? And to get 5 unknowns, we have to have 5 points, and then we can uniquely represent that curve. So to multiply 2 n degree polynomials, sorry, 2 n minus 1 degree polynomials, like n size polynomials, we would, like the output would be 2n minus 1 size polynomial, so 2n minus 2 degree polynomial basically. So we would require 2n minus 1 such points. And here it is like our A is degree 2 and B is degree 2. It's so our C would be degree 4. So it would have 5 unknowns, right? And then we have to have 5 samples. So number of samples are fixed. Like, because we want these 5 points of C, then only we can uniquely represent this curve. Otherwise, if there is one unknown, then we have a lot of infinity number of choice almost, right? Not infinity. If we have the field, then that field number of kind of choice, right?
So still, like these like samples, okay, so 5 would be enough, but like they don't uniquely represent the curve that you
It would, right? Because if I have 5 unknowns and 5 points, then we, like if 5 points are independent, then we have the unique representation of the curve, right? That is really needed for Tumkuk. It's kind of the base. And if you think for Karatsuba, it's also similar, because for Karatsuba, it is kind of, we are splitting in 2. So we have 2 into 2 minus 1, like points. That's why we needed 3 points, something like that. But yeah, I'll come back there. So it is with the point value, point representation, even though we have to do 2n minus 1 kind of point multiplication, but it still remains order n, right? Because it's not exponential, it's not n square, it's 2n minus 1. And after that, yeah, I went there. Oh yeah, so for point value to, from coefficient to point value representation, what we need for Tumkuk, that is called evaluation. This step is evaluation. There, by using this step, we go to this point value multiplication, point value representation. Then we do the multiplication, and we require an interpolation, which will get us back to the coefficient representation from the point value representation. And there, for that, we have like a n-length polynomial in Tumkuk, and we want to, like, this n-length polynomial is A and B. It has n-length means, I'm interchangeably using n-length and n minus 1 degree, but it's the same, okay? N-length means like n unknowns. That's why I feel it easier rather than n minus 1. So it's an n-length polynomial, it's another n-length polynomial. Then we can split this 2 n-length polynomial to k parts, okay? I'm explaining the generic one. There is like mostly in any scheme it is used either k is 3 or 4, Sever uses 4. So, but I do want the generic term so that I can mention like what will be the complexity for if you use, let's say, Tumkuk 5 or Tumkuk 8 or something. But yeah, now I am splitting here to k parts. This is like this. So here I make x to the power n minus k to y so that representation becomes a little bit easier. And we have this kind of polynomial now. Y is kind of a polynomial as well. But yeah, with this we have k-length polynomial now, like after the splitting. So what do we need? If we have k-length polynomial, how many points we would require to do the multiplication? Any guess? Go ahead. Oh, I'm so sorry. I shouldn't have. Yeah, okay. Yeah, it's 2k minus 1. Yeah, I'm not, habituated with this one. I keep forgetting. Okay.
You could also be tested actually who is awake to repeat the slides.
Oh yeah, that's true. Are you awake? Are you with me? Please ask question if you have any, okay? Okay, we have 2k minus 1 point. We would need those because we want to do a polynomial multiplication and it increases the length. We do need 2k minus 1 points. And then we do actually find out what would be the coefficient representation if we put this y1 to k minus 1 point. And that is what we do during evaluation, okay? And for evaluation, it's kind of a matrix vector multiplication. It's like this one. It looks like this. And this is the y term. This is the a0, a1, ak minus 1. Here we put some values. This y1, y2, yk minus 1, these are some values. But I'll say if I have 0, 1, 2, minus 1, 0, I'll check those first. And also an extra point infinity that will give me the biggest coefficient, this one. If we put 0, then we get a0, right? But if we put infinity, we get ak minus 1. We have an extra benefit. So we do always take, if we have if we have to pick three numbers, then we will, like, let's say we are doing Karatsuba, that is Tumkuk two-way multiplication. I'll choose 0, infinity, and 1. So we have less operations. We don't have to do any extra steps, because I have to do, this coefficient would get bigger if, this coefficient would get bigger if I choose bigger number, and then I have to do more operations that I don't want. So yeah, it's kind of very vague details, I would say. And then I have this evaluation step. This is the split, but for this we get this A1 to A1 and B1s. After that, I do multiplication, and this multiplication is cheap, that is the pointwise multiplication again, but we have 2k minus 1 points. And after that, I have interpolation. Interpolation is also very similar to evaluation, but it's kind of inverse. It looks like this one, and then we actually do this inverse multiplication. Yeah. Another thing is, like, to do this inverse, we need to have this, this inverse exist in the field, right? We need to exist this inverse to that ZQ if I use ZQ field then. But if it doesn't exist, we can also use some shift operation, and yeah, we can accommodate that, We can like shift it and keep the extra bit so that it doesn't get lost, basically. And that is one technique that is used when your modulus is power of 2, you don't have inverse, right? Because it's not a field. It's not a field. So you don't get inverse, you just make sure that you still get something which is equivalent to inverse, and that's how you do operation, basically. And yeah, with this, we have interpolation step, and also finally we have to reduce in the in this ring size, that is RQ, that is the ring which is used in lattice-based crypto. And then our complexity becomes like this, That is because we have 2k minus 1 steps here, and then by using Master's theorem, we get this complexity when our sub multiplication time is like n to the power e, which is n to the power log 2k minus 1 log k. K is the base there. Yeah, you can represent it that way too, right? So now our cost reduced from the school book one, and if your k is big enough, then it is small number, okay? It's less, for sure it's less than n square, but it can go towards as low as 1.5 or less than 5, is something like that. But it doesn't get you to just n or n log n, but it reduces quite a lot if you like use a big number. Let's say even if you use Tumkuk 4-way multiplication or 3-way multiplication, then this number is like log n to the power 5 by 3, right? Yeah, something like that. So it becomes cheaper. We are improving from school book to Karatsuba to Tumkuk, basically. And Tumkuk is like the Karatsuba actually is Tumkuk 2-way multiplication. It is the special case, basically. Although Karatsuba came first, then Tumkuk came. It's kind of a generalization of the Karatsuba method, and it is actually if you use bigger k, then it improves even more. Like your complexity gets lesser and lesser. And with this, I go to the entity, which is right now is used as the showstopper. Now, I first will use a good ring structure. Yeah, just wait a few minutes. This is ZQ by x to the power n minus 1. Please note that for Kuiper, it is plus 1. So it has like we need bit more for that. But for minus 1, it's easier. Here, that coefficient to point value representation, we use for that algorithm. Like that evaluation, we actually called entity, that is number theoretic transformation, and then inverse entity, that is that inverse how to go back from this point value representation to coefficient representation basically. And we have this multiplication. The good thing for entity, this multiplication is not 2k minus 1 or 2n minus 1, it is n. It just, you can do coefficient wise multiplication. It's nice. You have less operation.
Yeah, just based on the fact that you're using convolution and like something like that puts into another domain and then you go back and this is a multiplication, I would assume this like entity is something like Fourier transform alike thing.
It is FTT, it is FFT, okay. But it's in the field. FFT is in complex number, right? You have like your roots of unity kind of thing, that is a complex number there, but here it's a field element. But it's very much similar, you will be able to follow. It's because I did know FFT and then I transformed it to entity, so it's similar. So after that, yeah, are you guys following? Good. Now, to do this entity, I would require an nth root of unity in that field. And as we need this thing, we can't use entity when our n and q both have GCD 1, like n and q are not prime to each other, then we can't actually use that thing. And for Saber, it was n is like 256 and q is 2 to the power 13, so your GCD is the full thing. So you can't use entity for that. And that's why we had to do a lot of cool techniques to use to get equivalent or better result as Kyber. That is used in Saber basically. Okay, here I need nth root of unity in that field, and if I have that, I would need to do this matrix vector multiplication to transform from this coefficient this coefficient form to this point form. And this is omega is the nth root of unity here, okay? And as you can see, this matrix is very much structural, and that helps entity to become a very good algorithm, very efficient one. Because if we do like matrix vector multiplication, it's again n square, right? Because we have to do multiply every time, so it's not efficient. Yeah, n square. Or n cube. Oh no, n cube, right? If n square or n cube? It's matrix, okay. Yeah, if we have matrix vector, then it's again n square. So if we follow this method, then it wouldn't be efficient. So we have some techniques for this. We would again use divide and conquer. I have made it like as generic divide and conquer procedure as possible, but yeah, entity doesn't show in that way these days. Like for that, actually, you can split this coefficient from even and odd term, and then you can conquer it in this way, you know, like that omega is the values there, omega is the points there. And power of omegas are also those points which I mentioned during the first point representation, that we do need some points where we evaluate the polynomials. Here omegas are the point. And now we do divide and conquer, and this step we can do as many times as unless it becomes like 0, okay? So we can go full like binary search tree kind of thing. We can do it repeatedly as possible. And we have one thing, that is, as we have taken that good ring, that is x to the power n minus 1, then our omega to the power n is equals 1. So omega to the power n by 2, like if I have the half root kind of, then it is minus 1, right? Right? Because I am saying omega to the power n is 1, it is the highest one, its primitive root, then omega to the power n by 2 should be minus 1, unless it would have been, if omega to the power n by 2 is 1, then it's not nth primitive root, okay? So with that, I get this minus omega to the power j, where I evaluated this point, that becomes omega to the power n by 2 plus j. And that's how we can do this divide and conquer strategy basically. And this thing is the butterfly that is known very popularly, that entity butterfly. People try to optimize this component as much as possible to make this whole entity thing as efficient as possible. Because this is the main operation that is used like not only in post-quantum, it is used in FHE and it used in like in FFT form, it is being used in like signal transformation or signal transcription or whatever. Processor. Okay, thank you. There for a long time because it's a very known technique and very efficient one, and we have just made it usable for ourselves, just to give a new cool name that is entity, and we are using it. And with this, our complexity becomes n log n, and it is the most efficient one we have now. Because of this, this kind of split, we have n by 2 length. Here, it's a good thing. Like we can split it just 2 halves, and we have only 2 kind of operations, right? And please note that in Tumcook, we required more branching, right? Not only 2, and that's how it was expensive. But as here it's just 2, and we get to we can make kind of like a binary tree, so its time complexity reduces in that way, and the multiplication is just order of n, so whole complexity becomes order of n log n. It's very cheap, like the cheapest one available right now. And yeah, inverse entity is the same as well. It's just, you just have to do an inverse omega kind of operations there. And you need a scaling factor that is n inverse to get back to that domain. And that's all we have. We got an n log n algorithm for the whole polynomial multiplication. Because this entity is n log n, inverse entity is n log n, multiplication is order of n, then the whole thing is n log n, right? Yeah, I'm talking about complexity only. There we have constant, we have additional terms, and that makes it even complex. But as I mentioned, Kyber has a different ring that is x to the power n plus 1. So we can't use the exact entity I mentioned. We do require a nega-cyclic convolution instead of the cyclic one that we had. That was a nice kind of structure and all. Here, I do need a nega-cyclic convolution here instead of just entity. I do need nega-cyclic entity, and here as well nega-cyclic and inverse entity. Because of this choice, we do need 2nth root now in the field. Then only we can do this fancy stuff. That is pretty simple. It's not very hard, I would say. Like for nega-cyclic one, this is entity psi. I have denoted in that way. And this this psi is the 2nth root of unity. And then you can calculate this thing because psi squared now omega and psi to the power n is minus 1. It is like omega to the power n by 2, kind of. And now we have, oh no, psi to the power n is omega to the power n by n, basically. Yeah. Oh no, sorry, omega to the power n by 2. Sorry. Psi to the power 2n is omega to the power n, which is 1. And now, if we get this big psi, that is actually power of some psi's, that is 1 psi and this psi n minus 1. This thing we do require so that we can get back to the exact field, okay? So we have some extra dot product kind of operation, like vector-vector multiplication, but it is pretty simple, and we store psi's and power of psi's beforehand so that we don't have to compute them, and that's how we make it cheaper in the implementations. It is happen in, at least in software for sure. For hardware, sometimes people do compute this to make sure that you need less area when you don't care about computation time. then yeah, that's how you actually do that. You can actually not store Chi. You can all the Chis. You can just store one Chi and you can compute everything else, but then it becomes very expensive, very like after a few steps. And this is the inverse. This is the entity. This is still remains order of log n log n, and oh sorry, and this is the okay. This is the inverse entity step. This should be identity, and here we have to do an composition with Chi inverse, and that is basically the inverse of this thing. It's not much hard, so it's very simple, and we still have this n log n complexity with negacyclic convolution as well, and this is a kind of algorithm that is used in Kyber when it has a good modulus. That was that bigger modulus. 7681, I guess, but it might be wrong. But it was a 13-bit modulus when it has Kyber was using that in first rounds. That actually had that was able to use this entity, negacyclic entity, because it had 2nth root of unity, 5/12th root of unity in that field. And New Hope is another LWE based. It is ring LWE based key encapsulation mechanism. It was like I would say it is one of the oldest one which uses a very good structure and make it feasible kind of. But yeah, there were many more before as well. But New Hope was like, yeah, as the name suggests, it was New Hope. But later Kyber and others actually improved it a lot. And ring structure was like, yeah, it had structure and people thought that it might get broken at some point, although there is no such proofs yet. So yeah, New Hope also used this kind of method. But later Kyber actually uses something special that I will come back here. Now I have all these polynomial multiplications and their complexities. What we discussed, that is school book 1 is order of n square, Karatsuba is order of n log 3, and Tumcook KOA is this one. I mentioned the Tumcook 4-way because it is used in Sabre, so I just put it here. And then entity and negacyclic entity, okay? With that, I have all the complexities. Now, where what is used? Yeah, as now Kyber's modulus is 3329, that doesn't have the 2nth primitive root. It still uses this negacyclic entity, but it stops one layer early so that it doesn't need that primitive root, that specific one. It can use that omega and Chi's, sum of Chi's, then it works out, you know. You can stop 1-2 layers early if you don't have that exact primitive root, the one you want in the field. So it's kind of a new strategy they have shown that with that you can even improve, you know, with incomplete entity you can improve the time complexity. As I mentioned, that school book is very good if you have small n, right? But it becomes worse when you have big n. So for the last layer, they use this school book multiplication, and yeah, that's how it's done right now. And for Sabre, it has power of 2 modulus. It has good reduction. Like it doesn't have to do like any fancy modulus reduction, which Kyber has to do. Kyber has to use Barrett reduction, Montgomery reduction, and all those things so that it remains in the same field. But yeah, but it's still a order of n log n. It's not, it's polynomial time almost, right? It's very less expensive, so it actually still be very efficient. And Sabre used to use, or like native Sabre, I would say they used Tumcook 4-1 or Tumcook 4-way multiplication, polynomial multiplication. But later, another work actually showed that you can use entity, and anyway, you can use entity. But if you use a bigger prime where you can actually use entity for Sabre or such power of 2 numbers, then also you can make it efficient. In fact, it is efficient. This entity-based Sabre is efficient in terms of timing compared to the Tumcook 4-way one. But it needs way more area because you have to, now you have to store twiddle factors, like all the primitive roots in a bigger domain. So your numbers, like you need more basically stack memory or more area for hardware, so it becomes expensive in that way. But time-wise, it becomes better. I will not go to that details. It's for the future. Sure.
For Sabre, is there anything stopping us from just using an FFT and treating the rounding errors as additional noise?
Yeah, FFT, but you have to use then complex number, right? Yeah. Don't you think it's going to be expensive if you don't have?
Like latency-wise on a modern x64 CPU?
But you have to use it in the embedded devices when you don't have those, right?
I was asking, like, in general.
I'm not sure. I don't think it would be cheap, otherwise people would use it, but I'm not entirely sure why it's not used, Like Entity was proposed an alternative variant, kind of an improvement of FFT to and to use it on like when your field is finite. Yeah. It should be cheaper, but I'm not entirely sure.
Because, for example, what FFT libraries do, they use FFTs because they're faster than NFTs, because the libraries tend to be highly optimized.
I agree with you, but then you have to have that library, right?
Yeah, of course.
Yeah, but I'm not sure, people do use Entity, not FFT, and Entity is the field, like finite version of FFT basically, right? I'm not sure it's going to be cheap or not, but I'm not really sure. And I'm not aware of any work who does that, but there are floating point arithmetic, so I'm not sure. Probably there might be some, but I haven't used it yet, so I'm not very experienced.
There are also some side channel concerns with floating point representations. It's a bit trickier.
Okay, yeah.
They could be less constant time than
Yeah. Okay.
of course.
And with this part is done, and now I will go to the side channel as you have started.
Perfect.
I wanted to give you a 5 minutes break, but it's 12. I'm very slow. So I'll not give you 5-minute break, maybe take 1 minute. Okay. With this, I'll start the side channel attack part. You guys are with me, right? I hope it. Okay, as he mentioned, that side channel attack is very, I would say, very important topic for public key crypto especially, as you have a lot of, you have a long-term secret and all. And in fact, for cryptography, there are several side channel attacks. In fact, if you have a very good cryptanalysis, then it's mathematically secure. But if you implement it in a bad way, let's say your password, it checks like, yeah, it checks if you have given 0 or 1 for the first thingy, like there is attack, right? Do you guys know? Or not? Or maybe not. Okay, let's do a simple exercise then. Somebody choose 0 and 55. You can choose in your mind. And then multiply it with 52 and say who is done. Like raise your hand if you are done. Okay, then you choose 0, right? So it's a side channel attack. Yeah, people give a bit harder, but I think it's just before lunch. I will give it very simple. Okay, that is side channel attack. And polynomial multiplication is complex. And here I will talk about only power attack, because most of the lattice-based schemes, as we already knew that side channel attack is a big thing, especially timing attack, as this one was pretty easy to figure out, right? So constant time implementation was a must kind of thing. And that's why discrete Gaussian distribution was replaced by centered binomial distribution, so that it becomes, for sampling secret and error, so that it becomes easily constant time and you can't do timing attacks. And also there were Fujisaki Okamoto that is hard to make it secure. There used to be an and check, which doesn't check if you fail the first condition, then it becomes insecure again against timing attack. There are several timing attacks already on a lot of cryptography, even like cryptographic algorithm, also in post-quantum ones, also in the games. But I'll not talk about timing attacks, because those were made secure, like I would say, like in the very beginning when I even started working on it. Although there very recently a timing attack has been shown on Kyber. It is exploiting that compress, decompress, those compress functions and decode functions. So it's still possible, you know, finding timing attack, but the only solution to main timing attack, that is constant time implementation. And it's not, I would say it's hard, but it's simpler, relatively simpler, and I would say relatively cheaper as well compared to if you do have to find some countermeasures against other side channel attacks like power attacks. Okay, because you can get any information with power if you are like, you can check that your system is actually like operating on 0 or 1, right? It has different power, and that gives you the information basically about that element you are processing. It gives sometimes Hamming weight, sometimes Hamming distance, like yeah, it depends on the model you are choosing, but I'll just go through it. Yeah, that is the side channel attack that I gave the intro. This is a nice picture. It's not AI, so it's not that good, but it's a little bit okay. Okay, for power side channel attack, it gets the information from the device which is computing the cryptographic operations. Okay, and you get something which is related to the secret. And secret or secret related information, those are sensitive. If you get enough information, you can get back the secret basically. And how can you prevent that? Because we want to prevent the attack, right? We do want like the attack, but people will want some countermeasures, because if you show attack, yeah, it's cool, you would get a crypto paper, but after that, what? You have to show that, yeah, you can find a countermeasures as well. And we are doing the boring part for it. It's the countermeasure. No, first I will show an attack on, a very nice attack on Sabre and Kyber. They have exploited the polynomial multiplication, which I talked about in the first half of the talk. They could exploit Tumcook multiplication, and also the entity one. No multiplication is secure. You know, you can get back the secret after a certain traces, and then, yeah, you have the secret. The adversary has the secret. And how do we prevent that? For that, we use masking techniques. And in this part, I will talk about the masking techniques. How do you apply it on Sabre, Kyber, or any such lattice-based schemes, key encapsulation mechanisms especially, but you can also transfer a lot of results to digital signatures as well, you know. So, and lastly, on the top of it, I'll show a physical attack on it. So you can do an attack as well. But okay, first do the security. This is the masking. I'll just go through how it basically works. This is the first picture. This is an unmasked environment. You are doing this operation. It is very simple. You are taking input, doing XOR with S, and giving back the output. If you check how this is consuming, like how the device is consuming power for this operation, we simulate it like, yeah, you can see the power, you know. You can probe one of the operation and get to know like how much power it is consuming, and that is related to the secret S. Then you can, after a certain number of traces, you can find the secret S, okay? But if you do masking, there we split the shares. It's kind of MPC, okay? We split the sensitive information in multiple shares. It is kind of like secret sharing if you know about it. But it's, yeah, the idea came from the same field. But yeah, you can't merge the secrets anywhere, you know. You have to have multiple shares throughout the whole computation when you do masking. And this is how, like let's say S1 and S2 are two shares of the secret S, and S1 and S2 are independent with each other. You can get only the S if you merge it, and you don't merge it during the computation. So it remains safe. And like you will get two outputs. Sometimes you can merge those outputs because it's output public thing. But yeah, it will eventually should give you the same output as the first one, okay? Now, if you like do this side channel attack, then you get to see either of S1 and S2 kind of like probing model. I'm very simplifying the idea. It's not like as easy as I am saying, but it's the simplified idea of the masking and how it is modeled, because it's a provable security. It's very mathematical when you analyze it, and the proving is also very mathematical. But after that, you have to show it like experimentally how it remains secure, how it shows the security, right? So yeah. And now, yeah.
So what S1 and S2 are like shares of the secret?
Yes.
And so what do you do then? You just like send it through to different channels or something?
No, we use the same channel. It is not channel. It is the crypto. Like it's your device.
Okay.
Like we are not sending anything like that. We are sending just output 1 and output 2. That is through the channel. We can actually merge those output as well, because we don't think that output would have any information, because otherwise your crypto is not secure, right?
But what the masking then refers to actually to which part?
Masking is this part. You share the secret. This is very simplified example. It gets hard pretty quickly, you know. If you have multiple operations, it's just a XOR, so it's very simple. It looks very simple, but if you have multiple XOR and everything, and as you saw that post-quantum algorithm, that was pretty big, right? We have so many polynomial multiplication, we have hashes and all. So it's like we have to make sure we have multiple shares every time. So it's kind of, at least it would make twice as expensive, at least.
So basically, masking refers to the fact that you are not revealing part of your information.
Yes.
You are masking part of your information.
Yeah, it is like masking. Like you are masking your secret by like adding up noises. You can think like you sample S1 and like internally you sample S1 and you get S2 by doing S XOR S1. So it's kind of like you are adding noises, and that would give you 2 shares which seemingly independent, and it is like any random number. So it's not secret. Unless you merge those 2 up, it's not the secret. It's random. Now, how do you do T-order masking? Okay, for that, T-order masking means like the picture I showed that had first order masking. There we split twice. For T-order masking, we have to split T plus 1 times. Okay, and it is just generic idea of masking, because side channel attack wise, you can probably see like it's a model. In model, you can see like T shares. If you even see like T shares out of T plus 1 shares, then you can't get any information related to the sensitive value basically, because it's the same funda as the first one, right? But yeah, it's like it can prevent T-order side channel attacks, differential power attacks specifically, or correlation power attacks, those. So, you know, the theoretical model and the experiment, it's kind of be 2 separate field. We try to model mathematically how it works, but this idea actually works pretty well, this masking idea. And like if you increase the order of masking, then doing the side channel attack with that order, it becomes harder. So if you have less noise, you have to go for higher order masking. If you have a lot of noises in your system, then you don't have to go to higher order masking actually. Like it depends on how much noise you have, how much extra information are there, something like that, okay? And how good your power consumption, the machine, your oscilloscope is, how good it catches the power. That's also very important. If you don't have a good setup, you can't do the attack. So yeah, with that, for lattice-based key encapsulation mechanism or lattice-based digital signatures as well, we need 2 kind of masking techniques, which is arithmetic masking and Boolean masking. Arithmetic masking means we split the shares in S1 to ST, S0 to ST, like T plus 1 shares, but the relation in between S0 to ST with S is the summation of these shares on mod Q is the original secret S, okay? It is very good and it works very well. It is cheap when we do these operations like modular addition, modular subtraction, or modular multiplication, which is used in polynomial multiplications and all those arithmetic operations that were there, encoding, decoding, not the decoding or encoding, but all other ones like addition or subtraction, what were there, okay? And we need Boolean operations. We have a lot of Boolean operations because we use COSIC. COSIC is based on Boolean operations wholly. And we also have some other operation that is Boolean. If we do bit, like it is bitwise kind of operation. So if we have this kind of masking, those becomes easier. It is the simplest one and the oldest idea of the masking. That is like you just XOR all the shares and that gives you the original secret basically. That's the relation between this, but you never XOR them in the cryptographic, like in your masking algorithm, okay? And it is useful for all those bitwise operation I mentioned earlier. Now, how does the lattice-based algorithm which we want to protect looks like? It's not that simple as just a XOR, right? It's very complex and very big algorithm. I'll give a very brief overview how you can mask it, not too much details. And for that, you have like all these operations. And why decapsulation algorithm? Why not others? There are several other, right? Encapsulation, key generation and all. Because decapsulation operation has this long-term secret key. It's like non-ephemeral. So you use this secret key several times, maybe for a lot of months or a year. So we have to make sure that this secret remains safe, right? For a long, long time. And if the attacker gets the secret, then they can actually create the shared key, which is this HK prime C. And it can act like the decapsulation module, right? So you don't want that. And that's why we do masking. And the arithmetic operations are easy. How can you mask that? You just apply arithmetic masking. It's very linear. So it just, you just have to apply on all the arithmetic operations, okay? And here I have taken the decapsulation algorithm of Saber because it has less step and it's easier. And I did that, so I had everything with me. And that's why I picked this one for the first one, but I will show you the masked Kyber as well, so don't worry. And yeah, this is the arithmetic one. I will show one example how arithmetic masking is work. It's the simplest one. Like, let's say you are doing addition with x and y, and which is z, and x is only shared, okay? Because x has sensitive information in it, but your y is not, y is public or it's not, don't need to be masked. One example is this one, okay? H2 is a known constant, so it's not important to mask it, and we want to make sure like masking remains cheaper, right? So yeah, we don't mask that one. We just masked the x one and we keep y as it is because it's known and anybody can find it. So how the z share will look like? It should look like this. Z0 would be x0 plus y, and all others zi, which were 1 to t, would be the xi shares. But it's still secure because your x shares is the random ones, so it should be secure. So that's how you do masking when you have like one masked shares, one masked variables, and another one is unmasked, basically. You don't need to mask. And if y is masked, then also it's easy because you can do share-wise addition, like xi plus yi, kind of. Then it gets you the shares, okay? So it's easy. For multiplication, it might have been harder if you had x and y both are shared, but it's not the case in lattice-based crypto, luckily. So it's still like, it's still linear because we always have only one masked shares and another one is always, either public or you don't need to you don't have to mask it because it doesn't have any sensitive information in it. And that's why we can actually use this linear multiplication technique, because if you split x into x0 to xt, if you multiply with y, then you get back like all the shares of Zi's, right? Because it's linear. Is this okay? Okay, and that's how you do arithmetic masking, okay? And now we have Boolean masking that I'll not go in too much details. For Boolean masking actually, G and XOF, G is the hash, XOF is it's also Keccak based, okay? Both of them are Keccak based. You can use, there are so many good Keccak based masked algorithm, masked Keccak algorithm are there because Keccak is like it has been standard for a long time. There are so many masking work, so we could have used like all the masked implementation from there, and those are always Boolean masked. So you have to have this two masking, you know. And also for shift operation, if you do shift, that is always cheaper if you just do Boolean masking, because you just have to shift like all the bits except the bit you want, right? So that's cheaper. And that's here I have used this orange color to denote Boolean masking and blue color to denote arithmetic masking, okay, throughout the algorithm. And we do need some Boolean to arithmetic masking conversion, like converting Boolean shares to arithmetic shares, okay? Because if you had two different kind of shares, it doesn't merge, right? You can't act on other shares, so you have to have different conversion algorithm which will convert Boolean shares to arithmetic shares. And luckily, it's you can do inside an operation as well. And centered binomial operation, it's very cheap, but if you have like both Boolean masking and arithmetic masking, then like both kind of shares, then it becomes cheaper, okay? I have those slides, but as you can see, this is the whole centered binomial distribution basically. And here, this part you have actually Boolean masking, and we can do all the operation, that Hamming-Webb subtraction I mentioned, you can already do it with Boolean masking, okay? I'll not go to too much details, but if you are interested, you can ask me later. And this part, when you do subtraction by 4, as 4 is an arithmetic number, it's always cheaper if you can do it on the arithmetic shares. So here we do this operation on arithmetic shares, and in between we do this P2A conversion, okay, Boolean to arithmetic conversion. Although it looks very small, this is one of the most expensive component in this masking algorithm. And the next expensive component is this arithmetic to Boolean conversion. We do need that one too. Sadly, you know, it would have been better if we need only one. But here we have arithmetic shares, here we need Boolean shares. How can we get that? We have to do an arithmetic to Boolean conversion here. And this is one of another very expensive operation. These are the operation, those are very expensive, but it wasn't there. It has to be introduced due to masking and due to different kinds of masking. And if you wonder like why don't you use one kind of masking, it's more expensive. If you use this conversion, then it's cheaper, little bit cheaper. But we have to try use at least amount of conversion as possible so that it remains reasonably expensive, not very expensive. And I'll not go too much detail of that. I had prepared that A to B conversion algorithm, but do mind it. This A to B conversion algorithm is also a divide and conquer kind of algorithm that I mentioned in the beginning. So we do like divide and conquer kind of algorithm in computer science, and we do use that in cryptography. And this is how it works. It was an example of it. It's like you split input, then you do expand, secure, and you get those, and then you have the result. Okay, sorry, it was too fast. Okay, it looks like this, okay? It's just an example of A to B, just to show you that why it is expensive, okay? It has so many steps, like all of these are extra step, and this 3 thing, it is like our T is here, 3 basically. So if you have bigger bigger share masking order, then you will have like this number will increase, you know. So yeah, it depends on how many shares you have, what is your masking order basically, okay. So with this comes to the result. if you see that overhead factor it introduced for first order, it's not optimized for first order, so it's like 3x. But if you optimize for first order, it can become 2x or around 2x. It is overhead factor on unmasked one, okay? And for second order, third order, it gets increased. As you go for higher orders, it becomes very expensive. And it is an implementation on Cortex M4, the embedded device. So it is popularly used in post-quantum algorithm, as many of you may know. And after that, this is the Kyber algorithm. I'll not go details, sorry. Okay. And yeah, sorry for taking up much time. I'll try to wrap up as fast as I can. And this is the decapsulation algorithm of Kyber. It has much more steps. As you can see, this was the arithmetic to Boolean conversion, or that step, compression step for Sabre. But for Kyber, it is this big. And this operation and this operation, these two operations are very expensive. And it has more, like this has more steps, and it has like more, more such blocks which are non-linear. These are due to, Kyber has to sample secret and errors, a lot of errors. That's why it has those blocks, and those blocks are expensive for masking. So I have good results. This is the masking Sabre and masking Kyber result. If you see, those two algorithms was pretty similar in unmasked domain. But if you mask them, the Sabre is the purple one, and Kyber is the orange one. Kyber becomes like twice as expensive, at least, than Sabre. So if you need Kyber for like in embedded devices where actually you need side channel security, it's not very fast.
So when these results were obtained? So like
2022.
So it was before the final standards were out.
And I think it was announced or almost announced at that time. Like
So
NIST has decided. It was a bit too late, yeah. Because for first order, this result wasn't that bad, But if you go higher order, it becomes bad because Kyber has those Q prime modulus, and for masking prime modulus is not good, because you have to first convert to power of 2 domain, and then you can do your operations, something like that. And that's why it becomes expensive. It's not inherently like unmasked operation were cheap, right? And as it could use entity, that makes it even better. So for unmask, it was very much similar, but if you mask, you have to convert to power of 2 and then go back again for to Q to do your operations, so it becomes expensive.
So what NIST say about that? So do they have like a very like heated thread saying that
I think they made it standard for general purpose uses. You don't need masking always, right? You do need masking for embedded devices. I know many may disagree, but we do need some zoo elements, We do need some extra elements which you can use for embedded devices when you don't have much area or much memory. You do need masking there as well, because it's a publicly available device, so you can do side channel attack. Then if you can't handle masking, if you just give you the unmasked one, then you make attacker may compromise your device, right? So you may need one extra variant that is lightweight or masking friendly. And even NIST also sometimes, include extra algorithms, like they have standard ECC in 2008 or something, and later they were adding curves into their specification, right? As the crypto gets improved, they also modify their standards. So it's kind of, we need agility or something, like get more things to do like stuff when we need that, something like that. Probably we would require some. Go ahead.
Just another question. For Kyber, what would stop us from this modular switching from prime Q to power of 2Q? This would introduce some error, yeah. But then we wouldn't have a prime modulus anymore.
Then you don't have that cheap multiplication, right? The entity.
But then we can use
Yeah, you can use it, but then you change the algorithm.
No, just the entity.
Yeah, but it depends on entity.
Yeah, I know, but like it's.
Yes, its secret is stored in entity domain. You lose your speed. Yeah, you can use then
But then I feel like
that,
the performance
but
first and third order would be closer.
but then you change the parameter, you know, because then it becomes saver. It's not Kyber anymore.
I mean, your assumption is that's still different.
No.
I mean,
Yeah.
I'm talking about just for encapsulation or decapsulation, for example.
Maybe you can. I'm not sure. I still have to think. Probably I'll wrap up and then I'll think. Okay. Yeah, this is the result. But after that, you can still do an attack, physical attack, which we have shown. Like you can compromise this compression operation, and especially we have actually attacked that arithmetic to Boolean conversion algorithm with a fault attack. And this fault attack is introduced due to masking. It wasn't there when it was unmasked, okay? So, and it's kind of a cross attack. We call it cross attack. This attack is introduced, this fault attack is introduced due to masking. So, it is introduced from a countermeasure. So, yeah, this is kind of, I would say, it is an indication so that we still do have to do a lot of work on physical attack security so that it remains secure even like in given environment when you do need this kind of attack security, you know. You do know that your attacker can do this and that, and then you have to make sure like it can't do that basically. You don't need fault attack or side channel attack security everywhere, but you do need in some places. And you have to think about for those places as well, right? So I do think this area is still very unexplored because it's very new, right? Its implementation is still have timing attack vulnerability. So why, like, it's still need to be explored. This is the main message I have. You know, we have a lot of gap from the standardization from standardization to deployed all these algorithms to like in real world crypto systems, okay? We do have to work a lot for that. And with that, I have this conclusion. This is the thing that what I have explained, that is this key encapsulation mechanism, then the polynomial multiplication, which was one of the very expensive and native component to lattice-based key encapsulation mechanisms. And another thing is like we do need side channel security, and masking is one of the good provable and experimentally shown way to do that. And careful masking is also needed to make it as cheap as possible. But and also masking can actually change algorithmic performance of the lattice-based algorithm basically, as you can already saw. You have seen that, yes, mask saver is better than mask kyber, but and I'm not saying like mask saver is the best one available, you know, like we have also worked on several other learning with rounding-based key encapsulation mechanism, and we have shown that it's even better. So we do need a masking-friendly algorithm probably, and that would be very helpful for the applications where we do need masking and we don't have enough timing availability, or we don't have enough computation power, or that all those places. But it would be for probably for special purposes, you know. So with that, and yeah, we also still have to think about other physical attacks. Fault injection attack is the pretty basic one, you know, and we did also not very complex one. So we do need a lot of those analysis and countermeasures. Especially we don't have any fault attack countermeasures, you know. We do have some like a little bit, we do know a little bit about fault attack countermeasures from the classical crypto and other like RSA and all those classical crypto and all symmetric key crypto, sorry. And but that is like introducing redundancy and errors and all those. But Fujisek Okamoto transformation, that is a very, you know, very hard, like hard to protect component, I would say. And there has been so many attacks on countermeasures, so it's really need a compact analysis and countermeasures that I feel. And with this, I conclude my talk. Thank you. Thank you to be with me.